So welcome to the continuing videos for Math 1500 Calculus 1. So in this video, we've already seen how to take limits geometrically and how to deal with limits using a table of values, which we'll never see again because, as we mentioned, it can be a little bit misleading. What we're going to do here is talk about the rules that we're allowed to use automatically when it comes to limits. Now, we're not going to prove these rules because they require a little bit more formal definition than what we've already developed, but we are going to just state all these rules and then talk about how to use them and some of the nice consequences of them. So the first rule, actually throughout this, we're going to let C be a constant, and we're going to be talking about two specific functions, that being f of x and g of x. And all we're going to really care about those functions are that these two limits, the limit as x approaches a of f of x and the limit as x approaches a of g of x, both exist. What they're equal to won't matter for the way we're stating these limit laws. Obviously, they matter when it comes to the final answer, but in terms of the statements of the limit laws, their actual values won't be important. Just that they actually do give us some value. All right, so our first limit law that we're going to be talking about is the limit of a constant. So the limit of a constant. So remember, whenever we're dealing with a limit, we're asking what is the y value getting close to as the x values get close to a. So what are the y values getting close to? And if the function is a constant function, y is equal to c, then as x gets close to a, and in fact as x gets close to anything, the y values are not just getting close to c, but actually being equal to c. So that's how we deal with the limit of a constant. The next easiest function we can look at is the function y is equal to x. So we'll take a look at that one. And so again, we're asking if y is equal to x, as x approaches a, what is y approaching? Which is the same thing as saying as x approaches a, what is x approaching? Obviously that's equal to a. In fact, we can beef this up a little bit and talk about powers of x as well. So this one isn't as obvious, but it probably makes sense that as x gets really close to a, x to the n is getting really close to a to the n. Now for now, we're just going to say if n is a positive integer. Later on, we'll talk about exactly when we can say other things about that exponent. If we make it a fraction, if we make it something else, what can we say about that exponent? But for now, we're just going to stick to positive integers. All right, so these are the few ways of piecing it together. The next rule talks about, well, it's actually going to be three separate rules. So if we have the limit as x approaches a of f of x, and we're going to talk about three ways of piecing them together. Either we add them together, we subtract them, or we're going to multiply them of g of x. So the only thing we need here is that these two individual limits exist. The limit of f of x exists, and the limit of g of x exists. What they're equal to doesn't really matter for these rules anyway, and we're allowed to split them up. So that's the limit as x approaches a of f of x, and then either plus or minus or multiplying the limit as x approaches a of g of x. So as long as the limits individually exist, we can add them together, we can subtract them, we can multiply them by no real complications. All we need is that their limits individually exist. The one that gets a little bit more complicated, we'll talk about in a little bit. All right, so let's talk about the last one we're going to talk about before we make our first generalization, is what happens with a constant multiple. So if we have a constant multiple of a function, our next rule says as long as the limit exists, we can pull out that constant. So if you have a constant multiple here, you can factor that outside of the limit. The constant can come in the limit, outside the limit, it doesn't matter. All right, so let's talk about a consequence we can have for this, because there's a certain class of functions that we can create by taking powers of x, multiplying them by constants, and then adding and subtracting them, or multiplying them technically, although we usually think of it as adding and subtracting. And that's polynomials. And if you look at least these two rules, it looks like all we have to do is plug in the x is equal to a. There's some constants out here as well. So if we put all those things together, we get our first rule that says that if p of x is a polynomial, then the limit as x approaches a of p of x is equal to p of a. So whenever you're dealing with a polynomial, all you have to do is plug in whatever's coming into that limit, plug that number into the polynomial, and you'll automatically get your answer. Because of that, polynomials are super easy and boring, and we won't really look at them very much because they are that easy. That being said, when they do come up, just keep in mind that all you have to do is plug it in. All right, so we talked about adding functions, subtracting functions, and multiplying functions, but we conveniently left one out. So the limit as x approaches a of two functions being divided. So this is still under the condition that the individual limits exist, but there is an obvious, or probably obvious, issue that can arise when we actually take advantage of this particular limit law. So not only do we need that these two limits individually exist, we also need that we aren't dividing by zero. So provided the limit as x approaches a of g of x is not equal to 0. So we've dealt with all polynomials. We have a method of dealing with that. And once we take a polynomial and divide it by another polynomial, we can get an even bigger group of functions that we can look at. So if p and q are polynomials, then the limit as x approaches a of p of x over g of x is equal to p of a over q of a if q of a is not equal to 0. So for polynomials, plug it in, no problem. For rational functions, a polynomial divided by another polynomial, plug it in, and the only problem is if we're dividing by 0. If we're not dividing by 0, we automatically get our answer in that case as well. All right, so there's a couple more limit laws that have a similar idea where we might get some kind of restriction based on some kind of domain issue. And so 7 the limit as x approaches a of the nth root of x. So if we have the nth root of x, we do have to be careful here. There's a very obvious restriction. So once again, this is going to be equal to the nth root of a, provided that we don't have some kind of domain issue. So provided that n is odd. So if n is odd, cube roots, fifth roots, we don't have any domain issues. Or a is bigger than 0. If a is positive, we also don't have any domain issues, even if n is even. Now you might say, what about a equal to 0? So what happens if a is equal to 0? Well, let's think about the square root. Here's our square root function. The function exists at a is equal to 0. However, we're not talking about the function, we're talking about the limit. And as for the limit from the right might exist, but the limit from the left here, that limit does not exist. So the overall limit can't exist because the function, and hence the limit, doesn't exist from the left-hand side. So that's why we can't use a equals 0 if we're talking about the limit. However, we can talk about the right limit. So we can say the limit as x approaches 0 from the right of the nth root of x is equal to 0. If n is even. But if n is odd, if n is even, the overall limit at 0 doesn't exist because it doesn't exist from the left-hand side. All right, and we can extend this to more general functions too. Specifically, again, if n is odd, or the limit of x approaching a of f of x is bigger than 0, then the limit as x approaches a of the nth root of f of x is the nth root. We can bring that limit inside. Later on, we'll talk about how to extend these ideas to more general class of functions, but the idea of what we're doing here is, for the most part, unless we have some kind of domain issues, we want to just be able to plug in the function. We want to figure out when we can do that. It works for polynomials, it deals for rationals, it deals with square roots, and in general, that's a question we want to ask, although we'll deal with that in a later time. All right, so these are the limit laws, and we're going to talk about how to apply them in the next video.